This aspect of the video, we're going to talk about the distribution of elements in rocks, and we are going to fully concentrate on calculation of gains and losses during weathering. Now, we already know that the concerns of geochemistry has to do with the relative abundances of elements in rocks and in minerals. Then the second concern that Goldschmidt gave out was that you have to know the distribution of the elements as well. So this aspect, we're going to talk about how rocks are being distributed, the distribution of rocks, of elements in rocks. So let's assume that we have the soil profile. Let's assume that we have the soil profile with fresh rock. So let me call this aspect the fresh rock. Then let's say we have maybe a moderately weathered. Then we have, let's say, highly weathered. Let's just take this two for the meantime, highly weathered. Then this part, the part on top of the fresh rock or the bedrock is what we call the saprolite. Is what we call the saprolite. So what we want to do is we want to determine how much element has been lost from there because you know that the saprolite is a result of chemical weathering. So when this fresh rock tends to weather chemically, chemical weathering, when it tends to weather chemically, it forms the saprolite. So we want to know how much element has been lost from the fresh rock from these saprolites. This whole idea brings about the calculations of gains and losses during weathering. So we take a sample on some analysis that was made in the lab. Then based on that sample, we'll study how to make these calculations. Let's look at this data from a chemical analysis. So before you be able to do this calculation, that's the gains and loss, there is a need for you to first check if the total sums up to 100. So from here, we are seeing that the fresh sample one is the fresh rock, and two, three, four are the weathered materials, or what we call the saprolite. When you check the total, sample one is 100.07, and this is 99.1, 99.91, then whatever. Right. So you will not be able to use these values for calculation unless you convert these given values to 100. They have to sum up to 100 before you can even begin with your calculation. So first of all, you have to make sure that the the sum is up to 100. So for this particular case, let me take case one is the sample one is the fresh rock, and sample two, I'll take sample two as the weathered rock, right? The weathered aspect of the weathered material of the rock. So you have to first make sure you convert all these values to 100. So let me draw a column of table, a column over here. Name it as sample one, right? So I'm just going to show you how to convert these samples to 100. Convert these samples to 100. We are not going to do for everything because we'll take a major question, but the whole idea is for you to learn how to convert this to 100. All right. So first of all, because we want to convert to 100, so let's start with SiO2. For the sample one, its value is 71.54. But we want to express this in terms of 100. So we have this is what you are going to do. You are going to divide this 71.54 over 100.07. Then multiply this whole thing by 100. Multiply this whole thing by 100, then you should be getting something around 71.49. So we have this is equal to 71.49. That's for the SiO2. So 71.49. Then you do for let's do for aluminum as well. So we have 14.62 over 100.07. And multiply this whole thing by 100, and that gives we have 14.62 divided by 100. That gives 14.62. So we have 14.61. 14.61. So this is how you do the calculation goes. So let's try for K2O. So with that one, you'll be having 3.92 over 100.07 again by 100. And that should be given. That's 3.92. So that's 3.91. We have 3.91 for the K2O. Similar thing, you are going to do similar thing for the sample too. So with that one, let's start with the SiO2. This is the value for the SiO. So we have set 60.09 divided by 99.91. Then multiply this whole thing by 100. So 60.09 99.91 by 100. That gives 60.15. So 60.15. Then let's also do for the aluminum. 17. So the aluminum we have 17.31 divided by 99.91 and multiply this by 100. 17.31. That should be giving 17.33. So this is how you are going to convert make sure that the total come up to 100. So first of all, that's the first thing you should do. Check if the total sum up to 100. If it doesn't sum up to 100, then you can't go ahead and use this approach. So let's take this example and try. So the first thing you're supposed to do is to check if they sum up to 100. So that if they don't, you have to convert them to 100. So you realize that in this example, the sum is already up to 100. So there is no need for any conversion. Now, the next thing that is expected of you if you want to calculate this is to determine a certain factor from this. And usually the factor we consider is Al2O3, right? This is because during the weathering process, Al2O3 do not increase that much. Yeah, so that's the main reason why we choose the Al2O3. So if nothing is stated or no factor is given, you can use Al2O3 as your factor. So now, after getting Al2O3 as your factor, there is a need to find your weight factor, W. And the weight factor is simply going to be, since you are using Al2O3, it's simply going to be the percentage of Al2O3 in the fresh rock divided by the percentage of Al2O3 in the weathered material, which is the saprolite. So meaning that in this case, we have 12.3 divided by 26.3, and that gives 0.467. So this is our factor, 0.467. So now you generate additional three columns. The first column will be the amounts remaining in grams. The next one is the gain or loss, also in grams. Then the last column is the gain or loss, and, and this is in gram percent, right? In gram percent. So now how do we find for this amount remaining? In order to find for the amount remaining, you multiply your factor by the saprolite, the percentages of the saprolite. So the first instance, let's say SiO2, we have the saprolite percentage to be 35.1. You just multiply that by your factor, which is 0.467. Then you have 16.3, 16.3, not just 16.4. So we have, so let's say for SiO2, we have 0.467 by 0 by 35.1, and this gives 16.4. Then you do that, so we have 16.4. So I'm not going to do for all, you have to do that yourself. So this for the SiO2. This should be for, let's do for TiO2. So for that, we have 0.467 by 3.96, and that gives 1.0. 85, 1.85. So we have 1.85 here. The next one, Al2O3. So we have 0.467 by 26.3. And that should be giving us 12.3. So we have 12.3 in here. The next one is for Fe2O3. So with that we have 0.467 by 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 21.5, and that should be giving us minus 10, sorry, we have 10.04, 10.04. So we have 10.04. That's for amount remaining. So you do that for the remaining aspect. You do that for the remaining aspect. Now let's move to gain or loss in grams. So in order to calculate for the gain or loss in grams, you simply have to subtract the fresh from the amount remaining. So for SiO2, we have 16.4 minus 50.7, and that gives minus 34.3. For TiO2, we have 1.85 being subtract, then we have 3.19, and they should be giving you minus 1.34. So we have minus 34.3 here, minus 1.34. When you do that for this, you get 0. When you do that for this, you get minus 5.06. So this one's do for the remaining. Then finally, gain or loss in grams. You just simply have to divide the amount remaining in grams, the gain or loss in grams divided by the fresh, then multiply by 100. What do I mean by this? So for SiO2, we have minus 34.3 divided by 50.7, then multiply this by 100. And they should be equal to minus 67.6, right? Then for TiO2, we have minus 1.34 divided by 3.19, again by 100. Then you have minus 42.0. Let me do for Fe2O3. For that, you'll be having minus 5.06 divided by 3 point, divided by 15.1 by 100. And that will be giving minus 33.5. So here is 0, minus 67.6, minus 42, minus 33.5. So you do that for the I. So for the LOI, that's loss on ignition. Amount remaining is simply 0.467 by 4.4, and that gives 5.79. So for LOI, we have 5.79 here, 5.79. Then let's do for the gain or loss. So the gain or loss is simply 5.79 minus 1.70. So 5.79 minus 1.70, and that's 4.09 positive. So we have plus 4.09. And the percentage is simply 4.09 over 1.7 by 100. So by 100 divided by 1.7. That's 240.5. So we have plus 240.6. 242.6. Yeah, so you do for the remaining. Now the next thing is to find your sum. So you sum everything over here. So how do you know the value of the sum? So initially we said that our weight factor is 0.467. When I multiply this by 100, I'll be getting 46.7. And that will be your amount remaining. So 46.7. So when I sum everything over here, I should be getting this value. If there is something wrong, meaning that then you have to cross check. Then after getting 46.7, I subtract this from 100. So 100 minus 46.7, and that gives me 53.3 minus 53.3. Right. So I have 40, so I have 46.7 minus 100. That's minus 53.3. So minus 53.3. So when I sum everything over here up, I should be getting this value as well. So that's it. You can also be asked to rank this in terms of their magnitude. So in terms of their magnitude, here the values I have over here, ranking this in terms of magnitude, I'll rank P205 since it has 240.6%. Then the next one will be 6 for the SiO2. Then the next one will be TiO2. Then Fe2O3, then I come to Al2O3. Okay, the values are computed for. If you do all the computations, this ranking will change. So don't base on this ranking, just for you to get an idea. So do for the computations over here. Then based on your computations, you do your ranking. In the ranking, you don't consider the signs. You just look at the magnitude, you take absolute values of the gain or loss in percentage. So that's it under gain or loss.